So this is lecture number 2 of the four-part lecture on complex numbers. In the previous lecture, I went over what complex numbers are and how do you represent them in complex plane. Different types of representations, which are actually two types of representations, which are Cartesian representation or rectangular coordinate representation, and polar form of complex numbers. And I also showed how to go from Cartesian to polar and polar to Cartesian, and also discussed as you should be careful about if your number is located in the second quadrant on the complex plane or the third quadrant on the complex plane, then when you are going from rectangular coordinate or rectangular representation to polar representation, that you have to be careful about, as your calculator may give you incorrect angle, and you may have to add or subtract 180 degrees based on in which quadrant your complex number is located. So in this lecture, which is part 2, I'm going to go over the addition, subtraction, multiplication, and division of complex numbers. And I will show you how you're going to do these mathematical operations, in which form it is done, and some mistakes that I have seen students make while doing the arithmetic of complex numbers. I will let you know about that as well. So let me open my whiteboard. Okay. And before I move on to the arithmetic of complex numbers, one more thing that I should mention is if your complex number is located on the axis, then it is very easy to go from one form to the other form, instead of, even if you use the conversion that we discussed in lecture number 1, you can still find the same result as I will show you right now. But it is important, especially as an engineer, that you should be smart enough to do these things without going to the formula all the time. So you know that this is the real axis. All the positive real number will be on this. All the negative real number, which will be on the negative side. And this is the imaginary axis, and this is the negative imaginary axis. So all the j number are on the positive imaginary axis. All the negative j numbers will be on the negative imaginary axis. So if your number, of course, is located on the real axis, somewhere here, wherever, right? Let's say your number is x is equal to 2.5. You can also represent this as 2.5 plus j0, because the imaginary component is 0. And this is rectangular representation, Cartesian representation, or rectangular representation. How are you going to represent this number in the polar form? Very simple. 2.5, of course, is the magnitude, and the phase, of course, with respect to x-axis, it is on the x-axis, so phase is 0. So the polar form of the number is going to be 2.5 angle 0. And this is valid for any number that is located on the positive real axis. If a number is located on the positive imaginary axis, let's say over here, wherever, let's say the number is J3. So y is equal to J3. J3 or 3J or 3I, whatever, J and I are used both for to represent the complex number, imaginary numbers. Now in rectangular form, we can represent that as the value of real number is 0, and the imaginary part is J3. So 0 plus J3. And if you want to represent this number into polar form, then how are you going to do that? The magnitude is what? 3. This is the magnitude. The length of this vector, it's 3. And what is the phase? With respect to x-axis, it's making 90 degrees. So j always represent 90 degrees. If that is, if the number is on the positive j-axis. So 3 angle 90 degrees. And if you use the tangent inverse formula, then you're going to get the same thing. 3 angle 90 degrees. If your number is on negative real axis anywhere, let's assume that number is negative 7.67. How are you going to represent? First of all, in Cartesian form, you can also write this as negative 7.67 plus j0 because there is no imaginary component. And in the polar form, how are you going to represent this? What is the magnitude of this number? 7.67. That is the length of this vector. Let's say this value is negative 7.67 right here. So the length of the vector is 7.67. That's the magnitude. And what is the phase? Phase is from the x-axis. What angle it is traversing? 180 degrees. So 7.67 angle 180 degrees. So any number that is a negative real number in polar form, it will have an angle 180 degrees. Or negative 180 degrees, whatever you want to write. Positive is more commonly used. And last thing is any number that is on the imaginary axis, negative imaginary axis. Let's say this number is negative 5.5 j. So y will be equal to 0 minus j 5.5 in Cartesian form, 0 because the real component is 0, imaginary component is negative j 5.5. So the length of the vector is, magnitude is 5.5. And what is the phase? Since it is located on the negative y-axis, then if we go counterclockwise, your phase is going to be 270 degrees. However, as we discussed in the first lecture, that we give phase between 0 and 180 or 0 and negative 180, whichever is a smaller number. So you can give 5.5 angle 270 degrees, but it is more common to go clockwise and represent this phase, which is what? Negative 90 degrees. So 5.5, negative 90 degrees. That will be the polar form of any number that is located, or the phase of any number that is located on the negative imaginary axis. So keep this in mind. No need to go and start doing the conversion using the formula. Be smart and see where the number, if the number is located on any of these x, positive x, negative x, or positive y, negative y axes, then you can easily write down the imaginary, the polar form, or the Cartesian form of that number. Okay, now we're going to move on to the arithmetic of complex numbers. So first, if you're adding two complex numbers, addition. So let's say your number is a is equal to 2 plus j3 and b is equal to 5 plus j7. And you wanna do c is equal to a plus b. So if the numbers are given in the Cartesian form, you can very simply add real parts together of all the numbers that you're adding and then imaginary parts together. So in this case, it's going to be 2 plus 5. The result is going to be 2 plus 5, which is 7, plus j, 3 plus 7, which is 10. So the result is going to be 7 plus j 10. Very simple. And same goes for the subtraction. If I'm doing a minus b, then I'm going to subtract the real part of b from the real part of a, 2 minus 5, which is negative 3, and imaginary part of B from imaginary part of A. So 3 minus 7, which will be -4. So negative J4. Very simple and very easy. The problem is when your number is represented in polar form. So if 2 plus J3 is represented in polar form and 5 plus J7 is represented as polar form, let's say A is 2 plus J3, the magnitude of that in polar form is going to be 2a square plus 3 square. And the phase of that is going to be tangent inverse of 3 over 2, right? And since it is in the first quadrant, the phase is going to be the correct phase when you use the tangent inverse function. So let me write down that your magnitude of A is 4 plus 9, which is 13, is square root of 13. And then the phase of A is, I'm just going to write down this tangent inverse of 3 over 2. So in polar form, let's say the number is A, and the magnitude of A and phase of A. And likewise, in polar form, we represent B. So this is A in polar form, and let's say this is B in polar form. That is, you're going to calculate the magnitude of B, and you're going to determine the phase of B. Now, if you are adding or subtracting A plus B, or you're doing A minus B, whichever operation you are performing, you cannot do this. Make sure this is not allowed. So if you're doing C is equal to A plus B, you cannot do this. Magnitude of A plus magnitude of B, and then phase of A plus phase of B. So this is incorrect. So make sure, do not do that. And I have seen this mistake even made by advanced students in my power systems class, when we are discussing magnitude of currents or the magnitude of voltages. And if a question asks that the magnitude of current in this component is this much, magnitude of current in this component is this much, determine what is the magnitude of current in the third component. Then a student look at the circuit and they say, okay, maybe we can add the current together, or we can subtract the currents together. But they forget that the current is a complex. The current in that specific circuit is a complex quantity, and only magnitude is given. So what they do is they just go ahead and then they add both the magnitudes, and they determine that, okay, this is the magnitude of the third current, which is incorrect. You cannot do that. When the numbers are given in polar form, you must first convert them into Cartesian form. You must first convert them into Cartesian form. Now, many calculators can do addition and subtraction if the complex numbers are given in the polar form. And you can also create a small function that I will show you in the video lecture 4 in MATLAB, that can do the same job, that you just enter the complex number in polar form, and it will convert it into Cartesian form and give you the results, and then you can convert it back into the polar form. So if you're not using calculator, just for the understanding, let's assume right now so far we are not using calculator to do the addition or subtraction. So first you must convert each number into Cartesian or rectangular form, and then you're going to add or subtract by what we have discussed so far. And once you have the final result, then you're going to go back, if you have to convert it back, into the polar form. And if the input numbers are given usually in the polar form, then the output or the final result should also be in the polar form. So when you add them together or subtract them, you're going to get rectangular form. Then go ahead and convert the rectangular form into polar form, as we discussed in lecture number 1. That is what we were doing over here. Calculate the magnitude of the result, C, let's say, and calculate the phase associated with this. So if I convert this into polar form, let's say, I will have -3 square plus -4 square arctan of -4 over -3. And remember, I told you that be careful about this because this is located in the third quadrant on the complex plane. But if you use your calculator and perform this operation, negative over negative is going to become positive, and it's going to give you phase in the first quadrant. So this number is located right here. And then your phase is going to be over here. So this will be the phase that it's going to give you if you use your calculator. So you will have to adjust this. You're going to adjust this again, as we discussed. This hole is 180 degrees, -180, since we are going in the clockwise direction. So whatever phase you are going to get here, you are going to add -180 degrees because your phase is actually this theta. So here, basically what you can write, -180 degrees, the phase is going to be -180 plus arctan of -4 over -3. And of course, this is simply 9 plus 16, 25. So this is going to be 5. The magnitude is going to be 5. And the phase is going to be theta, which I'm showing in the picture. And that theta is going to be -180 degrees plus arctan, -4 over -3. Now, again, if your calculator can perform the job for you, you don't need to convert anything. If it can convert from polar to rectangular, rectangular to polar, then it will automatically take care of the angle. But I'm just telling you, in case you're using basic calculator and you're using the tangent inverse function, then be careful about that. Just look at the number where it is located and look at the angle of your final result. If your angle of the final result does not match with the location of the point on the complex plane, so the angle is positive and your point is located in the third quadrant where you know that the angle has to be between -90 and -180 degrees, then use your judgment and fix the angle and get the correct answer. Okay, so moving on, make sure again, do not make the mistake of adding and subtracting in the polar form, because you cannot add the magnitude and you cannot add the phases in the polar form, or subtract the magnitude and subtract the phases in the polar form. You have to go into Cartesian form first, do the addition and subtraction, and then convert it back into the polar form. All right, and the last two operations are multiplication. Multiplication can be done in either rectangular form or polar form. So let's say your A is 2 plus J3, and your B is 5 minus J5. So this is in the first quadrant, this is in the fourth quadrant. Y negative, X positive. And if I ask you that multiply A and B, then 2 plus J3 multiplied by 5 minus J5, and you're going to multiply each component separately. So 2 times 5 is 10. 2 times negative J5 is negative J10. 3 times 5, 15, and plus, J is here, so J15. And then J3 minus J5. Okay, so J times J. Remember in the last video I told you, J or I is -1, square root of -1. So J times J is square root of -1 times square root of -1, which will be -1. So J times J is -1, and then you have a negative sign here. So it's going to become positive. So +1, J times negative J is +1, 3 times 5, 15. So that simply will be 15, right? 1 times 15. And then you add or subtract real parts together and imaginary parts together. So 10 plus 15, 25. And 15 minus 10 is 5 plus J5. So that is going to be your final result. Okay, that's going to be your final result. If the numbers are given in polar form, let's say D is 5 angle 35 degrees and E is 6 angle -22 degrees. and you want d multiplied by e. It's very simple. You multiply the magnitudes and you add phases. So if numbers are given in polar form, you multiply magnitudes, you add phases. So 5 times 60, 5 times 6, 30, and 35 minus 22 is going to be 3, 3 minus 2, 130. So 30 angle 13 degrees. That's going to be your final result. So multiplication is pretty straightforward. It's much easier to do multiplication if the numbers are in polar form, because as you saw, you just multiply the magnitude and you add phases. But if it is given in rectangular form, you can still perform multiplication. A little bit lengthy process, but still it is doable. Sometimes, one can prefer to first convert the numbers that are given in the rectangular form into polar form, multiply them, and then go back to the rectangular form if it is convenient to do that. It's pretty simple in both ways, so it's upon you, whichever way you want to do it, but just do it correctly. And finally, division. So if the numbers are given in a rectangular coordinate, a is equal to 2 plus j3, b is equal to 5, let's say negative 5 minus j4. So first quadrant and third quadrant number. And I ask you, what will be the result of a over b? In other words, what is 2 plus j3 over negative 5 minus negative j4? Okay, the easiest way to do it is what we call multiply both numerator and denominator first by the complex conjugate of the denominator. What is complex conjugate? Complex conjugate. Complex conjugate is simply if you have a number a plus jb, you change the sign of the imaginary part. So the complex conjugate of this will become a minus jb. A minus jb, right? So you don't do anything with the real part, but only for the imaginary part you change the sign of that. So if you have a minus jb, you change it to a plus jb. So plus to minus or minus to plus for only the imaginary part. That becomes the complex conjugate of that complex number. So here we perform multiplication and division. Of course, we're doing multiplication and division, so it's not going to change the original number. Negative 5 plus j4 divided by negative 5 plus j4. We multiply and divide by the complex conjugate. Okay, so let's look at the numerator first. 2 plus j3, negative 5 plus j4. Like we did in our last slide, 2 times negative 5, negative 10. 2 times j4 plus j8. j3 times negative 5 minus j15. And j3 plus j4, j times j is negative 1. And 4 times 3 is 12, so negative 12. That's going to give me negative 10 minus negative 12, negative 22. And 15 minus 8 is 7. So negative 22 minus j7, that's my numerator. So this is the result of my numerator. As far as denominator is concerned, observe what's going to happen when you multiply a number by its complex conjugate. Negative 5 times negative 5, 25. Negative 5 times j4, negative j, 20. Negative j4 times negative 5, positive j, 20. And negative j4 plus j4, negative j times j, j times j is negative 1. So negative 1 times negative is positive, and 4 times 4 is 16. So plus 16. Observe positive J20, negative J20 cancelled out, and you get only 25 plus 16, which will be 41. So anytime you multiply a complex number by its conjugate, you will always end up with a real number. You will always end up with a real number anytime you multiply a complex number by its conjugate. So now this C is going to be negative 22 minus J7 over 41. And your result is simply negative 22 over 41, the real part of the number of the result, and negative J7 over 41, the imaginary part of the number. And this will be your result of the division. Negative 22 over 41, real part, and negative J7 over 41, the imaginary part. Okay, so this is how you're going to do if the numbers are in rectangular form, and this is a little cumbersome to do. Observe, if the number is given in polar form, so 5 angle 55 degrees, let's say, in the first quadrant, and let's say 2.5, just to make it simpler, 2.5 angle negative, let's say negative 110 degrees in the third quadrant. So I have the first number in the first quadrant and the second number in the third quadrant. And I want to do again the same thing, A over B. 5 angle 55 degrees over 2.5 angle negative 110 degrees. When the numbers are given in the polar form, it's the same thing as multiplication. In multiplication, you multiply the magnitudes, you add the phases, and that will be your final result. In division, you divide the magnitudes, so 5 over 2.5, which will be 2, and you subtract the denominator phase from the numerator. You subtract the phase of the denominator by the phase of the numerator, and that will be your final phase. So 55 minus negative 110. So minus negative 110 is going to become plus 110. So your final result is going to be 2 angle 165 degrees, right? 165 degrees. And that will be your result. So observe how easy it is to do multiplication, well, especially division, how easy it is to do division if the numbers are given in polar form. If the numbers are given in rectangular form, you first multiply by the complex conjugate of the denominator, both numerator and denominator, and then simplify it. So again, not extremely hard, but a little bit of work. So many times it's easier if you're performing division, and if the numbers are given in rectangular form, it's easier first to convert the number in polar form, then divide them, and then go ahead and convert it back into rectangular form. So if I have to convert this back into rectangular form, my real part is going to be what? 2 cosine of 165 degrees. And my imaginary part is going to be 2 sine of 165 degrees. So my number, C, will be 2 cosine 165 degrees plus J 2 sine 165 degrees, which is pretty straightforward, of course. So generally people prefer to convert the number from rectangular form to polar form, then perform the division operation, and then go back to the rectangular form. But whichever way you find it easy, you can do it. Again, the basic idea of these lectures is understanding, because again, most of the time you're using calculator or you're using MATLAB or any other programming language, and many of those languages can perform all these operations by themselves, or you can create functions, as I will show you, to perform these operations. But if you have the understanding of complex numbers, you're not going to be scared of complex numbers. You will always perform the correct operation, and you will always know based on the location of the point on the complex plane if your answer seems correct or if it seems incorrect. So I will see you in the third lecture where we're going to go over some advanced topics especially if you are electrical engineer, mechanical engineer, or one of the engineering field that you use transfer functions, you use, especially electrical engineering, electrical circuits for the sinusoidal steady state analysis. Then how do we deal with those circuits, and how to deal with the transfer functions? We're going to discuss that in the third lecture. So it's going to be a little advanced lecture. And if you are, you are studying at the basic level, then I think the first two lectures should be good for you. And the fourth lecture, if you want to, do stuff in MATLAB, then watch the fourth lecture. Third lecture may not be very helpful for you, but for my program, electrical and computer engineering technology, I'll highly recommend all the students, especially the electrical student, well, computer students who are taking circuits as well. I highly recommend all those students to watch all 4 lectures, and hopefully is going to help them taking the fear out of this complex number, which I see very frequently in pretty much all the courses. All right. Hope this lecture is going to help you.